where do the ideas go that never quite make it onto the engineering roadmap?
Oh, man. That question, I mean, that haunts almost every engineering manager or plant supervisor working today, right?
Mhm.
Whether they actually say it out loud or not. You can walk the floor of literally any industrial facility and see, the ghosts of those unbuilt ideas just sitting in the margins of everything they do.
Right. Well, welcome to today's broadcast here on Chesterton Radio in Atchison, Kansas. We are settling in for a deep dive that I think is going to hit very close to home for anyone listening who works in a technical, industrial, or manufacturing space.
Absolutely.
I want you to picture the typical engineering firm or maybe the manufacturing floor you might be sitting in or managing right now. Somewhere in that building or, perhaps just across the hall, there is a whiteboard.
Oh, there's always a whiteboard.
Always. Or maybe it's a shared digital workspace or, I don't know, a forgotten manila folder sitting in the bottom drawer of a desk. And it is completely filled to the brim with ideas.
And very often, I think people forget this, those are highly viable, mathematically sound concepts. They aren't just fantasies or wishful thinking.
Right. They're valuable, innovative ideas. Maybe it's a concept for like automating a clunky, repetitive manual process on the assembly line that's causing ergonomic injuries. Or maybe it's a custom testing rig that would make quality assurance 10 times faster and more accurate. Or honestly, maybe it's just a clever mechanical improvement to an existing thermal management system.
Yeah, these are solid concepts, but they suffer from one fatal, basically insurmountable flaw. They simply lack the time, the prioritization, or the internal engineering resources to ever actually be executed.
Exactly, because in the corporate manufacturing world, time and personnel are rigidly finite resources.
Right, and the critical path will always, always win the battle for those resources. If an idea isn't directly tied to, keeping the lights on or hitting this immediate quarter's revenue target or solving some catastrophic crisis that is currently halting production, it just gets sidelined.
Which makes sense, right?
Yeah, totally. That isn't a failure of imagination on the part of the management. It is just the harsh reality of corporate triage. I mean, you have to feed the beast that pays the bills today before you can build the machine of tomorrow.
I used to think of the standard corporate research and development pipeline as like a busy, high-speed highway.
Yeah.
If an idea isn't moving at 70 miles an hour on the critical path, it just gets pulled over to the shoulder and abandoned.
That's a great way to put it.
But looking at the sources we are exploring today, I think a better analogy is actually an industrial pressure relief valve.
Okay, I like that. How so?
Well, in any pressurized system, let's say a massive steam boiler, you have your main turbine that is doing the critical work of generating power, right? But you also have smaller relief valves. They don't drive the main engine, but they are absolutely vital because they safely bleed off the pent-up pressure of the system without risking a core explosion.
Right, they keep the whole thing from blowing up.
Exactly. So today, we are talking about finding that pressure relief valve for your engineering team's pent-up innovation. We're exploring a highly effective yet often completely overlooked solution to this exact problem of the idea graveyard.
And the mechanism we're analyzing today comes directly from the academic world, specifically the Benedictine College Mechanical Engineering Senior Design Program.
Which happens to be located right here in Atchison.
Right here in town. And what really merits our deep dive today is the underlying architecture of this program. Because it is fundamentally not designed merely as, like, an educational hurdle for the students. It's actually engineered from the ground up to function as a high-value functional release valve for that exact corporate backlog you just described.
Wow.
Yeah, it provides this dedicated, highly structured, and heavily scrutinized environment where those ideas parked in the desk drawer can finally be subjected to the rigors of actual physics and fabricated into reality.
Okay, let me stop you there and play devil's advocate for a moment. Because when a listener, let's say a seasoned plant manager, hears the phrase college project, there is an immediate and very specific mental image that pops up.
Oh, sure.
You think of a theoretical thesis paper, you think of a very nice, polished PowerPoint presentation, or maybe a fragile little 3D printed plastic model that cracks in half if you look at it wrong or drop it on a hard floor.
Right, the science fair trope.
Exactly. But reading through the structural documentation for the Benedictine Mechanical Engineering capstone, we are talking about a completely different species of output here, aren't we?
We really are. We need to thoroughly break down the true nature of what a mechanical engineering capstone actually demands at this level. Because the word capstone itself implies the crowning achievement, the final heavy piece of masonry that locks the entire arch into place.
Oh, I like that.
Yeah. For these mechanical engineering students, this stripped 2-semester program is the crucible. It is where they basically have to prove their readiness to step out of the theoretical environment of the classroom, where, the answers are hidden in the back of the textbook, and become actual practicing professional engineers.
So they can't just rely on theoretical knowledge anymore.
Exactly. They are required to synthesize all their prior coursework in thermodynamics, fluid mechanics, material science, kinematics, all of it. Combine it with independent, unguided research, and apply it to an open-ended, real-world industrial problem where there is no known correct answer yet.
And they are doing this in teams, right? Partnering directly with industrial companies who step into the role of the official sponsor.
That's right. And the timeline governing this partnership is incredibly rigid. I mean, this is not a loose, work-at-your-own-pace extracurricular club where deadlines slide just because midterms are coming up.
Right, real-world constraints.
Exactly.
Yeah.
Runs precisely and unforgivingly on the academic calendar, beginning in September and terminating in April.
And the pacing of that timeline is actually crucial to understanding the mechanics of why the end results are so robust, from what I'm seeing. According to the program's documentation, the machinery starts moving in the summer when sponsors submit their applications.
Yep.
Then, at the tail end of August, the project is officially assigned to a student team, and that team holds their initial scoping meeting with the sponsor.
Right, and that kicks off the first major phase of the operation. So from September through early December, which encompasses essentially the entire fall semester, the focus is restricted purely to design development, rigorous mathematical analysis, and basic proof-of-concept prototyping.
Meaning they are strictly forbidden from just walking into the machine shop on day one, grabbing a welding torch, and trying to stick pieces of metal together to see what looks good.
Oh, absolutely. If you try to build before the math is proven, you are inviting catastrophic failure. I mean, in professional engineering disciplines, that kind of ad hoc fabrication is a cardinal sin.
Yeah, that makes sense.
That fall semester is all about wrestling with the underlying physics of the problem. They are calculating the maximum load capacities of different alloys. They are running finite element analysis software to simulate shear stress and thermal expansion.
Wow. So really deep in the weeds.
Very deep. They are testing materials theoretically to understand fatigue cycles over thousands of uses. The entire goal of those first 4 months is making absolutely certain that the underlying mechanics are flawless on paper before a single piece of expensive stock material is ever even ordered.
Okay, so following that intensive theoretical phase, there is a distinct hard shift in the curriculum. Late January through April, so the spring semester, is dedicated almost entirely to physical construction, iterative testing, and refinement.
The fun part.
Right. They transition from the digital models and the whiteboards to actually fabricating the final product. And then in early May, there is the formal final project handoff to the corporate sponsor.
And this separation of phases really highlights why your earlier point about fragile plastic models is so important to dispel. The required deliverables for this capstone program are physical, functional prototypes.
Not just concepts.
Exactly. The academic requirement dictates that the students have to successfully build the exact mechanism they spent the entire fall mathematically proving would work.
And we actually have some incredibly compelling visual evidence of this physical reality in the source material provided. There is a photograph of a completed project that a student team built a few years ago.
So the rail cart, yeah?
Yeah, it's this specialized rail cart designed for an interactive museum exhibit. When you analyze the geometry and the build quality of this cart, it instantly shatters the illusion that these are, flimsy academic science fair projects.
The structural integrity visible in that specific build is just striking.
Let me paint a picture of this for you, the listener, as you're tuning in from your commute or your office. Imagine a heavy-duty, bright yellow metal chassis. It is immensely robust, clearly fabricated from thick tubular steel, welded and bolted with obvious precision.
And it's not on little wheels, right?
No. It doesn't sit on caster wheels. It is designed to sit on actual, real-world, heavy-gauge steel railroad tracks. Mounted on top of this bright yellow chassis is a beautifully finished, thick wooden platform designed to hold human weight safely.
Which is a whole different level of liability.
Totally. There are dual black seats, proper, thickly padded industrial operator seats, and they actually have heavy-duty safety seatbelts installed. And then, in the exact center of the platform, there is a substantial black mechanical housing.
Covering all the moving parts.
Exactly. That housing covers the internal drive mechanisms, the chains, the gears, and protruding from it are these long, heavy yellow hand levers that the operators would pump back and forth to propel the cart down the tracks.
It looks professional.
It really does. If you saw this sitting in a warehouse, you would just assume it was a piece of specialized industrial equipment ordered out of a high-end commercial catalog.
And analyzing that one rail cart really reveals the staggering intersection of disciplines required to execute a project of that caliber. I mean, you are looking at advanced structural engineering to ensure the chassis doesn't buckle under dynamic loads.
Yeah.
You have human factors and ergonomic considerations dictating the placement, height, and resistance of those pumping levers so the operators don't injure their shoulders. You have strict safety protocols necessitating the seatbelt and the shielding over the pinch points in the drive chain.
Which is huge for a public exhibit.
Exactly. Plus, you have materials science dictating how the steel interfaces with the wooden platform to account for different rates of thermal expansion and vibration dampening. And you have the core mechanical drive system housed in the center, converting reciprocal motion into rotary motion.
That is, that's a complex, multi-layered physical reality. It is heavy, it is dangerous if designed poorly, it is fully functional, and it was entirely engineered and built by these students.
Completely by the students.
So I am looking at this photograph and putting myself in the shoes of a skeptical engineering director. I can imagine them thinking, okay, the visual is impressive. Students can build a sturdy, cool-looking cart for a museum. That's a fun, novel project. But my factory floor isn't a museum.
Right. A very fair point.
My processes run 24/7 under massive thermal and kinetic stress. How do the academic requirements of this college actually force these students to act like a heavily insured professional engineering firm rather than just, an advanced shop class having fun with steel tubing?
Well, the mechanism that forces that professional compliance is the strict governance of the program's evaluation parameters. The university faculty, specifically the capstone instructor, Alyssa Ledoux, and the department chair, Dr. Patrick O'Malley, do not simply hand the students a corporate credit card, point them to the machine shop, and say, good luck.
That would be a disaster.
It would be. The academic rubric actually requires the students to produce a comprehensive, industry-standard design and documentation package alongside the physical prototype. Every single design choice, from the thickness of a weld to the specific carbon content of a bolt, must be mathematically and procedurally justified in writing and defended in front of a panel.
Wow. So they are essentially simulating the exact bureaucratic friction, the liability checks, and the brutal accountability of the real-world industrial sector.
Exactly. And because the academic requirements impose such rigorous, uncompromising standards, it leads directly to what might be the most brilliant structural constraint of the entire capstone program.
Which is?
That constraint dictates the exact types of industrial problems that are even allowed to be accepted for sponsorship in the first place.
Okay, which brings us to a phrase in the program overview that initially, honestly, threw me for a loop. If you read the documentation detailing what kind of projects these students take on, there is one specific, highly intentional phrase.
Non-critical.
Yes. It states that the students partner with companies to design and prototype a technical solution to a non-critical problem at the sponsor site.
The term non-critical is the operational linchpin of this entire collaboration.
I have to admit, at first glance, the word non-critical sounds like a massive demotion.
Oh, sure, I get that.
To a layperson or even a busy manager, it sounds like you are giving the college students the menial busy work, the leftover scraps that no one actually cares about. Why would a company invest time in something labeled non-critical?
But as we unpack the mechanics of industrial workflows, it becomes glaringly obvious that this non-critical designation is actually the program's greatest strategic advantage.
Walk me through that.
To understand the brilliance of the non-critical rule, we really have to examine the psychology and the operational realities of a corporate sponsor. For any manufacturing plant, industrial facility, or engineering firm, the absolute highest hurdle to pure innovation is operational risk.
Operational risk.
Right. Think about a massive automotive assembly line. That line is the critical path. Every station is timed to the second. If you introduce a new, untested robotic arm onto that active line and it suffers a software glitch or a mechanical jam, the line stops.
And when a line stops.
Exactly. When a critical path assembly line stops, the company bleeds capital at a terrifying rate, often thousands or tens of thousands of dollars every single minute. The risk profile of experimenting on a critical system is simply unacceptable.
Wow.
You just cannot let a team of college students, no matter how brilliant, test their prototype on a system that pays the company's payroll.
Right. You certainly can't walk up to a student team and say, hey, go ahead and rewire the main packaging arm servo motors and we'll just hope it boots up correctly by Tuesday morning shift. The liability is insane.
Completely insane. By explicitly mandating that the problem must be non-critical, the capstone program completely severs the project from the company's revenue-generating critical path. Operational risk immediately drops to absolute zero.
Zero. It effectively builds a blast wall between the student's innovation and the company's bottom line. It creates a safe sandbox.
A fully isolated, consequence-free sandbox
Yeah.
designed for pure engineering exploration. And this is the precise mechanism that finally unlocks those back-burner projects we mentioned at the start of our deep dive.
I see.
The crucial distinction listeners need to internalize is that just because a problem is non-critical to the daily survival of the factory does not mean the solution is non-valuable to the company's future.
Okay, let's ground this in the muddy reality of a factory floor. What do those high-value, non-critical back-burner projects actually look like in practice?
Good question.
The source material gives us several perfect archetypes. One major category is automating a legacy manual process. Imagine a facility where you have a worker whose sole job is to manually lift, orient, and place a 40-pound metal casting onto a conveyor belt 50 times an hour, 8 hours a day.
Brutal work.
Exactly. The job is currently getting done, the line is moving, therefore, it is not a critical crisis today. But it is wildly inefficient. It is a looming ergonomic nightmare that will eventually result in a workers' compensation claim, and it is honestly a terrible use of human labor.
Right. And that scenario represents the perfect non-critical problem. Another excellent archetype is the development of a completely new machine, a novel testing system, or an early-stage product concept.
Like R&D stuff.
Exactly. Suppose a company has a theoretical idea for a radically different type of valve that could open up a new market sector. The executive team wants to explore it, but the internal R&D engineers are drowning in maintenance requests for the existing product lines.
You just don't have the time.
They simply do not have the hundreds of hours required to draft, build, and test a proof of concept for a valve that might not even work. Or consider testing improvements on an existing running system without halting current production. A company might hypothesize, we think we can make our industrial thermal management system 15% more energy efficient by changing the heat sink geometry, but we don't have the internal bandwidth or the budget to build a dedicated standalone test rig just to prove it.
The psychological dynamic here is absolutely fascinating to me. As an engineering manager, by intentionally taking away that life or death, if this fails, the company goes under pressure,
Right.
you actually cultivate the perfect mental environment for pure, unadulterated engineering problem solving.
It really is a massive psychological relief for the corporate sponsor. You aren't constantly pacing around, looking over the student's shoulders, sweating profusely about your quarterly metrics or your personal bonus being tied to their immediate success.
Right. You are handing them a genuine, complex problem, and you are granting them the temporal and mental space to actually solve it from first principles.
And that unpressured space is the exact catalyst that allows the students to act like true engineers rather than just reactive technicians. They have the luxury of time to proceed through the rigorous design phases, the exhaustive theoretical testing, and the complex failure analysis.
All without a corporate vice president breathing down their necks demanding a quick duct tape fix by Friday afternoon.
Exactly. The non-critical designation protects the integrity of the engineering process itself.
So, if identifying a non-critical problem is the secret sauce to unlocking this resource, what exactly does a well-crafted non-critical project look like on paper?
That's the million-dollar question.
Because if you are a listener who is currently thinking about tapping into this program, you can't just send an email saying, build me a robot. You have to submit a formal proposal. And looking at the actual request for proposal, the RFP template provided by the university, it is incredibly revealing.
It really is.
It meticulously dissects the anatomy of a perfect engineering project.
The structure of that RFP template is essentially a masterclass in scoping industrial engineering work. It forces the prospective sponsor to be incredibly precise, clinical, and exhaustive about what they're actually asking for.
It divides it up, right?
Yes, it divides the exact project deliverables into two distinct, equally important categories: physical deliverables and documentation deliverables.
Okay, so on the physical side of the ledger, the sponsor is required to specify the scale of the required object. Are they looking for a fully functional, full-scale prototype like that heavy-duty yellow rail cart we talked about that they can immediately use? Or if they are asking the students to redesign the hull of a massive cargo ship, are they looking for a scaled-down, geometrically accurate model for wind tunnel or hydro testing?
Right, but the physical object is really only half the equation. The documentation requirements listed in the template are arguably just as valuable, if not more so, than the physical prototype itself.
Really? More valuable?
Yeah. In many ways, yes. The template mandates a comprehensive design and analysis report detailing the physics, a complete user manual for safe operation, and crucially, a complete manufacturing drawing package.
Okay, I want to pause and explain that last term for the listeners who might be on the business side rather than the engineering side. A complete manufacturing drawing package. That phrase is huge. What does that actually mean?
It's everything.
It means the sponsor isn't just receiving a one-off magical contraption held together by duct tape, zip ties, and hope with no idea how to recreate it. They're receiving the actual CAD files, the computer-aided design models.
The raw data.
They're receiving the precise blueprints, the exact material specifications, the wiring diagrams. It means the sponsor can take that digital package, hand it to their own internal manufacturing team, or email it to an external commercial machine shop in Ohio and confidently say, build me 50 more of these exact machines.
And that level of documentation is the precise dividing line between a fun school project and professional engineering consulting. The students are legally required by the course to deliver a fully replicable, heavily documented, scalable solution.
That is just incredible value.
It is. However, to fully understand the RFP, contrasting this ideal scope with what makes a terrible project is equally eliminating. Based on the strict academic timeline we discussed, remember September to May, and this vital non-critical operational rule, there are specific categories of engineering problems that are inherently disastrous fits for this program.
Safety critical systems are the first thing that jumps to my mind. I mean, you cannot outsource human life to a college course.
Precisely. If the failure of the requested prototypes results in a catastrophic safety event on a factory floor, for instance, designing the primary load-bearing winch for a manned construction crane, you absolutely cannot hand that to a student team.
Oh, definitely not.
The corporate liability, the insurance nightmare, and the ethical implications are entirely prohibitive. Furthermore, projects tied to immediate, rigid commercial deadlines are guaranteed to fail in this structure.
Because of the timeline.
Right. If your company needs a new sorting solution fully integrated, tested, and running on the floor by November to meet a massive holiday order, the capstone program is useless to you. Why? Because according to the academic calendar, the students are still in their theoretical math and analysis phase in November. They won't even order the steel until January.
Wow, okay. So the cadence of the work is entirely dictated by the academic rhythm of the university, not the frantic fiscal rhythm of the corporate world.
Exactly. The sponsor must completely submit to and respect that academic rhythm, or the partnership will just collapse.
Let's bring this back to the listener. If you are sitting in your office right now, staring at your whiteboard of forgotten ideas, what is the exact litmus test you should run your ideas through before submitting a proposal?
Good question.
How do you know if an idea is actually ready to be handed over to a team of engineers? The RFP template gives us a brilliant clue. It requires the sponsor to provide a detailed bulleted list of needs, quantifiable specs, and target metrics. And then, totally separate from that, it asks for a list of additional desired features, which they define as wants and stretch goals. For the non-engineers out there, how do you separate a hard, quantifiable spec from a stretch goal in a way that actually sets these students up to succeed?
That exact separation is the hallmark of competent engineering management. A quantifiable specification is a binary, mathematically verifiable metric. The machine either achieves it or the machine fails.
Okay, give me an example.
For example, the new automated lifting arm must be able to lift a payload of exactly 50 pounds. It must complete one full lift cycle in under 12 seconds, and the entire base must fit within a physical footprint of 4 feet by 4 feet. Those are hard, quantifiable specs.
Right, there's no gray area there.
Exactly. If the final arm lifts 49 pounds, or it takes 13 seconds, the engineering project has failed. A stretch goal, on the other hand, is qualitative or optimization-based. We would like the arm to lift 60 pounds if possible without increasing the motor size, and we would like the operator interface to feature a digital touchscreen instead of physical analog buttons.
Oh, that makes total sense. You also mentioned calculating tolerances earlier. For a listener who isn't a machinist, we aren't just talking about measuring a piece of wood twice and cutting it once, are we? What does a tolerance actually mean in the context of these specs?
Good clarification. A tolerance is the exact allowable margin of physical error before a manufactured part simply will not fit or function. If you are designing a steel shaft that needs to slide inside a steel cylinder, you can't just say, make them both 2 inches wide, because the friction will cause them to seize instantly. You have to calculate the tolerance. Perhaps the shaft must be 1.995 inches, plus or minus 0.02 of an inch. If the students don't calculate those tolerances perfectly in the fall, the physical parts they order in the spring simply won't assemble.
Wow. That gives the students a very clear binary finish line to cross with the required specs, but also provides them the creative room to over-deliver and show off their skills if they discover an elegant solution for the stretch goals.
Exactly. And the failure point for many sponsors is an inability to define those metrics. If a sponsor submits a proposal that vaguely states, we need a machine that makes our sorting process faster and better, that is not a scoped engineering problem. That is a wish.
Better isn't a number.
Right. It is impossible to engineer better. The corporate sponsor has to do the heavy intellectual work of defining the physics, the boundaries, and the specific metrics of the problem before the students can ever begin to engineer this solution.
So, assuming a project is properly scoped, the physics are defined, and you've separated your required specs from your hopeful dreams, the conversation naturally has to turn to the bottom line.
It always does.
Because at the end of the day, business is business. Industrial facilities don't operate on charity, they operate on budgets. And this is where the Benedictine capstone program transitions from being a nice academic exercise to making undeniable, almost aggressive financial and strategic sense for the sponsor.
Oh, absolutely.
Let's delve into the economic value here, because the financial parameters are frankly astonishing.
The precise financial model governing these projects is clearly and transparently outlined in the university materials, and it revolves around one central, highly unusual fact. The final price point for the sponsor entirely excludes any labor costs.
Hold on, let me emphasize that. 0 labor costs. No billable hours.
None.
That single fact alone should make any project manager or financial controller listening right now sit up and pay attention.
It's unheard of in the professional world. The corporate sponsors are solely responsible for funding the raw material costs required to physically build their specific prototype. And the documentation provides a historically accurate, typical range for those material costs. Usually falls somewhere between $3,000 to $12,000.
Okay, and that massive variance depends entirely on the mechanical complexity and the required component quality of the desired product, right?
Exactly.
I mean, the math on that is intuitive. If your prototype requires high-grade aerospace-rated aluminum, specialized pneumatic actuators, and precision optical sensors, you're obviously going to be pushing closer to that $12,000 mark.
Right.
But if your project requires standard tubular carbon steel, basic off-the-shelf electric motors, and simple relay switches, you're going to sit on the much lower end of that spectrum. But either way, you are only writing a check for the raw physical ingredients.
Which is just wild when you calculate the return on investment, the ROI, based on that model. The leverage is staggering. Let's create a conservative hypothetical here.
Yeah.
A company spends exactly $6,000 on materials for a custom automated testing rig.
Okay.
For that $6,000, what do they receive at the end of May? They receive a fully engineered, fabricated, functional, physical machine. They receive the exhaustive mathematical analysis proving exactly why the machine operates safely. And they receive the complete CAD drawings and manufacturing blueprints required to build 10 more.
Wow.
If that exact same company took that exact same non-critical problem to a traditional external engineering consultancy firm in Kansas City or Chicago, the final bill, which would include the firm's overhead, the partner's profit margin, the drafter's billable hours, and the fabrication markup, would easily run into the tens of thousands of dollars.
Oh, easily.
Depending on the prestige of the firm, it could easily push into the six-figure territory for a fully documented prototype.
It's essentially an off-site corporate R&D department operating on a subscription model, where your only subscription fee is the literal wholesale cost of the raw steel, the bolts, and the microchips.
That's a great way to think about it.
But as compelling as the math is, the financial savings on the physical prototype itself are really only half of the strategic value proposition here. There is a massive hidden ROI that the source material explicitly highlights, which might be even more valuable than the machine itself, the talent pipeline.
Yes. The official benefits list provided to sponsors explicitly mentions the opportunity to screen potential employees. This addresses one of the most painful operational bottlenecks in modern engineering management: hiring competent junior staff.
I really want to talk about that pain point. Think about the traditional, incredibly flawed hiring process for a junior engineer right out of college. You get a stack of resumes. You look at a kid with a 4.0 GPA. You bring them in for a couple of one-hour interviews in a conference room. They wear a nice suit. They answer your behavioral questions perfectly. Maybe you give them a theoretical technical test on a whiteboard, which they ace. So you hire them, you pay them a full salary, give them benefits, and put them on the floor.
And then reality sets in.
And within 2 weeks, you realize they are a disaster. They design a bracket that is geometrically flawless on the computer, but physically impossible to actually machine because they didn't realize a CNC tool head can't reach the inner corner.
Oh, I've seen that happen so many times.
Right. Or they script bolts because they don't understand torque in the real world. Or worse, they are arrogant, they can't take criticism, and they alienate your entire machinist team.
It is a massive financial and cultural gamble every single time you hire, based on a resume and a brief interview. The cost of a bad engineering hire is astronomical when you factor in the onboarding time, the damaged materials, and the inevitable severance. Sponsoring a capstone project fundamentally changes that dynamic. It serves as the ultimate 9-month pressure-tested job interview. The sponsor gets a front-row seat to watch a specific team of students tackle a complex, frustrating, highly constrained real-world problem over an extended period.
You essentially get to see them bleed a little bit.
You observe their reactions to genuine adversity. How does the lead student handle the design review when a professional engineer brutally questions the math behind their load calculations? Do they get defensive or do they adapt?
That's a huge tell.
Right. How does the team pivot when a crucial vendor unexpectedly delays a part shipment in February, threatening their entire build schedule? How effectively and how professionally do they communicate with you, the corporate sponsor, when things go wrong?
Because things will go wrong.
Always. You aren't just evaluating their ability to solve an equation, you're evaluating their work ethic, their practical technical competence, their resilience, and their interpersonal soft skills in a live-fire environment over the course of nearly a year.
The implication is so obvious. If you are monitoring a team of 4 students, and you notice that one particular student is constantly the one solving the bottlenecks, keeping the communication clear, and demonstrating a deep, intuitive grasp of the mechanics, you have the absolute inside track to hire a known superstar in May when they graduate.
You've already done the vetting.
You are hiring an engineer who is already intimately familiar with your company's specific processes, your communication culture, and your technical needs. Plus, the program materials note another intrinsic benefit. This partnership constitutes a deeply meaningful contribution to the engineering profession itself.
It really does.
Sponsors are given the direct opportunity to share their specific industrial best practices with these students. You are literally helping to train the next generation of American engineers to approach problems the right way, your way.
It is the definition of a symbiotic ecosystem. The students receive invaluable first-hand experience wrestling with a real industrial need, interacting directly with working professionals, and developing critical project management and physical fabrication skills that a textbook simply cannot teach. And simultaneously, the corporate sponsor receives a radically de-risked prototype, a solved technical problem, and a prolonged, risk-free evaluation of top-tier emerging engineering talent.
I follow the logic entirely. I see the immense financial value, the incredibly low cost of entry, and the strategic brilliance of the talent pipeline. But I know my audience.
Oh.
If you are an engineering director or plant manager listening to this right now, you are probably glancing at your overflowing Outlook calendar and wincing.
Valid.
When I read phrases in the brochure like mentorship, active participant, and sharing best practices, my immediate cynical reaction is to worry about my own bandwidth. Let's be brutally honest. Does sponsoring a team become an unpaid second job for the sponsor?
That is universally the most common and frankly the most valid concern that any prospective corporate sponsor harbors.
Because if I have a factory to run, I simply cannot have a team of 21-year-olds calling my cell phone every day at 3 p.m. asking me how to calibrate a torque wrench or where to buy aluminum stock.
No, you can't. And they fear being dragged into the weeds of micromanagement. However, The architecture of the Benedictine program explicitly anticipates and prevents that scenario. The interaction between the sponsor and the students is highly structured, formalized, and remarkably efficient. It absolutely does not devolve into a daily, grinding text message chain.
Okay, let's break down that exact structure, because the specific touchpoints between the sponsor and the student team are not arbitrary. They directly mirror the formal project management standards used in major industrial and defense sectors, don't they?
They do. The RFP template outlines the specific mandatory review meetings that define the entire relationship. The engagement kicks off with a site tour, allowing the students to physically walk the factory floor, see the environment, and understand the contextual reality of the problem they are solving.
Makes sense. Start with the context.
Right. Following that, there are three major formal academic hurdles: the preliminary design review, or PDR, the critical design review, or CDR, and the final design review, or FDR. And the year culminates in the final product demonstration.
Let's do some translation for the layperson, or perhaps the business manager who hasn't been deep in the engineering trenches for a few decades. What exactly is the functional difference between a PDR and a CDR? Why are these specific milestones so critical that they dictate the entire flow of the year?
Well, these acronyms, PDR and CDR, originate from the aerospace and defense industries, specifically organizations like NASA and the DoD, where mistakes cost billions of dollars in human lives. A preliminary design review, or PDR, occurs early in the fall semester. At this stage, the students present their initial conceptual approaches, the foundational mathematics, and the overall proposed architecture of the solution. The primary purpose of the PDR is to ensure that the students have deeply, accurately understood the sponsor's requirements and to confirm they are heading in a generally correct direction before they waste hundreds of hours refining the microscopic details.
Ah, okay. The sponsor reviews this presentation essentially to say, yes, conceptually, this approach solves my problem. Proceed.
Exactly.
It's the ultimate measure twice, cut once checkpoint before the serious, laborious CAD drafting begins.
Exactly that. Then, significantly later in the timeline, usually at the end of the fall semester, comes the critical design review, the CDR.
And this is the big one.
The CDR is the heavy, brutal, uncompromising milestone. At the CDR stage, the design must be 100% complete. Every single bolt must be specified by grade and length. Every mechanical tolerance must be calculated. Every material alloy must be selected and justified. The students must mathematically prove, beyond a shadow of a doubt, that their final design will meet every single one of those quantifiable specs we discussed earlier. Once the sponsor and the faculty approve the CDR, the design is officially frozen.
Wait, frozen? What happens if they need to change something after the design is frozen?
They can't, not without massive repercussions. That is the point of freezing the design. If you change the length of one structural beam after CDR, it changes the weight of the machine, which changes the center of gravity, which changes the required torque of the motor, which changes the electrical draw, which might blow the circuit.
Oh, wow. It is a cascading failure.
Exactly. The CDR ensures that the students have thought of every cascade before they buy the metal. Once frozen, the team moves out of the theoretical realm and into procurement and physical fabrication for the spring.
This reveals the genius of the time management aspect. By utilizing these formal industry standard review gates, the sponsor is never being asked to micromanage the day-to-day CAD drafting or the machine shop hours.
Not at all.
They are simply acting as the executive client and the final approval authority at pre-scheduled, highly concentrated intervals. You show up for the PDR, you review their presentation packet, you offer your expert industrial feedback, and then you completely step back and let them work independently until the CDR.
And the program literature is very clear on this dynamic. It states that sponsors are invited to be active participants to the extent they desire, but the student team is responsible for managing the project and will check in at those critical points to ensure they are meeting the customer's needs.
That is so reassuring.
You are never left in the dark wondering if they are building a spaceship instead of a sorting arm, but you are also fiercely protected from having to hold their hands through the math. Furthermore, there is a massive logistical and academic safety net built into the process before the project even officially begins.
Which brings us to the submission logistics. Let's cover those practical details so our listeners know how the timeline actually operates. The proposal submission window for companies opens in March, and it strictly closes on August 1st, right before the academic year spins up.
And here is where that safety net deploys. The materials indicate that after a corporate proposal is submitted, the capstone course instructor, Alyssa Ledoux, will personally be in touch with the sponsor within 1 week.
Oh, wow.
The instructor's explicit job at this phase is to gain a deeper, nuanced understanding of the customer's needs, clarify any vague metrics, and actively help the sponsor work out the project details so that it perfectly fits the academic constraints.
That is a massive relief. It means the university faculty is doing the heavy lifting of ensuring the scope is appropriate, safe, and viable before the students ever even see the proposal.
Absolutely.
You aren't just tossing a half-baked PDF into an academic black box, crossing your fingers, and hoping a bunch of 21-year-olds can decipher your factory's needs. The faculty is actively, professionally shaping your project to ensure it fits the academic requirements, which simultaneously guarantees a highly useful, executable outcome for you, the sponsor.
It is a meticulously managed process from day one. It removes the daunting managerial burden from the corporate sponsor and places it squarely on the academic structure of the university, which is exactly where it belongs.
This has been an incredibly enlightening deep dive. We've covered a tremendous amount of ground today. We've unpacked the rigorous, unforgiving academic structure of the capstone. We've explored the counterintuitive brilliance of the non-critical operational sandbox and how it eliminates corporate risk. We've broken down the staggering economic ROI of receiving aerospace-level engineering documentation for the mere cost of raw materials. And we've detailed the highly structured, low-burden, collaborative process that protects the sponsor's time.
We really went through it all.
As we bring this broadcast full circle, I want to invite you, the listener, to do something right now. Think back to the very beginning of our conversation. Think back to that whiteboard sitting in your office or that forgotten digital folder buried on your hard drive. What brilliant, viable ideas are currently stagnating in your organization right now?
What is that one specific project, that ergonomic fix, that new testing rig, that automated arm that you know is a matter of mathematical certainty would make your facility safer, more efficient, or more productive, but you just haven't had the time, the internal bandwidth, or the budget to pull it off the shoulder of the highway and get it moving?
I want to leave you with a final thought to mull over as you head back to the floor or finish your commute. In the industrial sector, we often condition ourselves to believe that the gap between a stagnant idea and a functional physical prototype is purely a matter of millions of dollars, massive corporate reorganization, and endless budget approvals.
Right, we think it's impossible.
But sometimes it isn't a lack of massive resources at all. Sometimes it is simply a lack of the right collaborative environment.
The profound realization here is that the solution to your lingering engineering problem might not be an agonizingly expensive external consultancy firm, but rather a team of hungry, capable, heavily supervised students sitting in a classroom in Atchison, Kansas, waiting for a complex problem to prove themselves on.
If that thought sparks something for you, or if you mentally matched an idea on your whiteboard to the parameters we discussed today, I highly encourage you to look into this further. You can examine photographs of past physical projects, review the actual detailed RFP template we spent time dissecting, and find all the logistical details on the Benedictine College Engineering Senior Design webpage.
It's definitely worth checking out.
Remember, the proposal window opens in March, so right now is the perfect time to start evaluating that backlog of ideas and writing down your quantifiable specs. We aren't here to give you a sales pitch. We just want to shine a bright light on a genuinely brilliant, highly structured mechanism for getting good ideas built. Thank you for joining us for this deep dive here on Chesterton Radio. Until next time, keep looking for the pressure relief valves in your own systems.